In the last video, we talked about basics of vectors, and what vectors are, what is the difference between a vector and a scalar, and the very basic properties of these vectors. Let's say, operation that is very important and useful in physics and mathematics is the dot product. The dot product, or sometimes called as the scalar product. So this is what we want to cover today. So let's first remind ourselves how we can show a vector in a 3D Cartesian coordinate. So imagine here we have our three-dimensional coordinate. I show that with x and y and z. And as we said, we always can have our unity vector, which is a vector with a magnitude of 1. That's what is called unity. And then we call that I hat if it's in the x direction, or j hat, or k hat. And these names are just the notation we are using, ijk. You could also call them anything. It's also common that sometimes in textbooks they refer to this I as for example, e in the direction of x hat, or any other notation that they can have. What I just want you to understand is that we have this concept of a unity vector, which has a magnitude of 1. It's in the direction of each axis, yeah? And these three are perpendicular to each other in the Cartesian coordinate, because the axes are perpendicular to each other here, okay? So, now imagine we have an arbitrary vector A, for example, like this. This is our vector. Now, we could think of the projection of this vector on each of the axes, x, y, z. And then think of those projected values as the components of this A vector. Yeah? So what do I mean by that? So this is now our vector A. If we try to project it like this in this space, this x and y plane, yeah, then we end up with these two vectors. One vector like this, and one like this, till here. And this one has the ax magnitude, and it is in the direction of I hat. So if I want to show it as a vector, I show it as ax times the unity vector I hat. Yeah. Then this one in the direction of y, then similarly can say it is like a of y times j hat. And now if we project the vector A on the z-axis, then similarly we will have the az times k hat. So these are the projected vectors on each axis from the original A vector. In other terms, if we write the vector A in terms of its components, we can write A equals the AX I hat. So this is the vector, yeah, the vector in the direction of x-axis, plus the AY J hat plus the AZ K hat. Now, remember this A of x, A of y, A of z are scalar values, so they are just numbers. And I hat, j hat, and k hat, these are the unity vectors. So, and the summation of these three vectors gives us the original vector, right? So, this is the idea of the projection. The projection of one vector onto other coordinate axis. Some people call it projection, or you could also think of collapsing. Yeah? So what happens if we collapse the vector A on the other vectors, or in this case, the axis? Yeah? In fact, we could ask, if I have a vector, if I have an arbitrary vector, what would be the value of the projection of this vector on a certain axis? Yeah. So then we are looking for this AX value, for example. So, and this is where the idea of the dot product becomes interesting. So we have this concept of the dot product. We use the dot product to find the projected values. So we can already see that the result of the dot product is a scalar, not a vector. So for example, if I want to have the Ix value, what should I do? I should do a dot product of the vector A and the unity vector of I, or the unity vector in the x direction, and what I get is the AX value, or the projected value, right? So let's try to write it. So if I have the vector A and I use a dot product, yeah, so how we show it is with a dot times this I hat, the result will be the AX. And this AX is a scalar, so a number. And you can do the same thing for the other axis. So vector A dot product j hat gives us the AY, and similarly A dot product k hat gives us A of z. So every time I want to know the value of the projected vector, I just have to calculate the dot product in that direction. Now, I just briefly also show the representation, let's say, of this product in terms of the angles. Now, see, we have this vector A, and this vector obviously has also some angle with each of the planes, or with each of the axes. So imagine this vector A with the axis x makes an angle of alpha, then A with the z vector, with the z axis, makes the vector the angle gamma, and the A with the y would have a vector the angle of beta. So we have obviously now three angles of alpha, beta, and gamma. And now we can talk about this collapsing of projection also in terms of the angles. Yeah. So for example, if I have the vector A and then I collapse it on this axis X, what do I get? It's the value of the magnitude of A times the cosine of alpha. Yeah. So that's also then the AX value. So then why not? Here, when we talk about A dot I hat, AX, this also equals to the magnitude of A, or write it like this, times cosine of alpha. And so similarly, this is A cosine of beta. So if I multiply the magnitude of A times the cosine of the angle that the vector A makes with the axis Y, then I get the dot product, or the projected value, components of A in the Y direction. And with the same logic, this is what? This is magnitude of A times cosine of gamma, which is the angle that A makes with the axis Z. So far we talked about the projection of A on the X, Y, and Z axes. But let's generalize this topic. What if we have a vector A, and then we have another arbitrary, and not necessarily orthogonal, just another arbitrary vector, let's call it B. And we want to know what is the projection of this A on the B vector. Yeah? So in other term, we want to say vector A dot product vector B. So first thing we can say already here is that, okay, these two vectors make some angle together. Let's call it alpha. And from mathematics, we can already say that then A times B, A dot product B, should be the magnitude of A, the magnitude of B, times the cosine of the angle that these two vectors make with each other. So at this point, I want to first say or mention some laws of this dot product. And then we can continue with the notation of the linear algebraic way of writing the dot product. So there are some rules here for the dot product. One is that it is the dot product is distributive. So what do we mean by that? So imagine we have a vector A, and then we have a dot product of the vectors B plus C. Yeah. So we learned from the previous video the B is a vector, C is a vector, and the addition is also a vector. So now we have the dot product of A vector to that vector, and the result will be a scalar. Okay. Now, what do I mean that the dot product is distributive? I mean that here we have A dot B plus C. We can write this as A dot B plus A dot C. So we are allowed to distribute A to this parenthesis of B dot C and write it as A dot B plus A dot C. Okay, cool. Another property of the dot product is that it is associative. Associative. Yeah? So what do we mean here is that, for example, if we have the vector A dot product, a scalar alpha times the vector B, what do we get? Okay. So we talked about the scalar times a vector in the previous session, that this gives us another vector, and which is in the direction of B. Well, if alpha is positive, and if in the other direction if it is negative, and the magnitude of B will be multiplied by the alpha, which is a number. Yeah. Now we have a vector which is alpha B, and now we have the dot product of A as a vector to that vector. Okay. Now what do we get here? Actually, since alpha is only a scalar, it can come out of this parenthesis and we can write it as this. So alpha multiplied R, and then we take the dot product with vector B. And since alpha is a scalar, we can even write this as alpha multiplied by the dot product of A and B. So we can play and change the position of this alpha as it is only a scalar. If it was a vector a vector, it wouldn't be that simple. Yeah? Okay, so now knowing these rules, I can actually calculate the dot product of A and B in another way. So I can write A as it is, dot product, and how can we represent B in terms of the unity vectors? We learned this before. So this is Bx, I hat, By, J hat, and then Bz, K hat. Now, knowing the rules that the dot product is associative and distributive, I can then distribute this A to these terms, yeah, one by one, and knowing that the Bx, By, and Bz are only scalars, like alpha, so we can actually change them the positions and write it again like this. So I can actually write this as Bx A dot I hat plus By A dot J hat plus Bz A dot K hat. Yeah? Now we learned this before. What is A dot I hat? This is the projection of A on the x-axis. Yeah? So that we learned this will be AX. And this will be a Y. And A dot K hat will give us a Z. Yeah? So we can rewrite this as Bx AX. Now don't forget, these are scalar values, so it's just a multiplication of two numbers. Yeah? So then By AY plus Bz AZ. So what does that mean? It means if we want the dot product of two vectors, it's enough that we just multiply the corresponding components, like the x components or the y components and the z components, and then sum them up. So this is very easy. I think it's very useful if we now make an example. So let's say we have a vector A, and A is 2i hat, 3j hat, and minus 1k hat. Yeah? And we have another vector B, again some random values I wrote here. So 4i hat minus why not 1 over 2 j hat plus 4k hat. Okay. Now we want to calculate the dot product of these two vectors. Yeah. So A dot B. So according to what we just learned is that we need to multiply the relevant values. So what do we do here is that, so ax times bx, so 2 times 4. Yeah? This 2 times 4, ax and bx. 2 times 4 plus the ay and by multiplied together. So this gives us 3 times. Be careful here. This is minus 1/2. And similarly for the z values, it is here minus 1, and this is 4. Yep. So minus 1 times 4. Now I can write this as 2 times 4, 8, minus 3/2, minus 4. This is 4 minus 3 over 2. And this is 5 over 2, 2.5. So the dot product of these two vectors gives me a scalar. It's a number. To extend this notation of A and B, of the dot product of A and B, I would like to write it like this. So if I have A dot product B, as we just derived, we can write it as the summation of the corresponding components, right? So we could also write it as the summation over I of component ith times bth. Yeah? So that means get the x, for example, I is 1. This is the first component, ax, and then bx. You multiply them. Then you sum it, then I is 2 with the next one, a2, b2, or in other words, ay, by, and so on. Yeah? Now, something funny here is that these are just scalars, yeah? ai and bi. So we can change the order here, because they're just the scalars. So I can actually write this as the summation over I of bi and ai. This is also the same. And what do I get here? This is actually then b, vector b, times a. So we just proved here that a dot b equals b dot a in the dot product. And this is also a very interesting property of the dot product. And it also makes sense because it is only a scalar, so it shouldn't matter if we have the dot product of a and b or b and a. And Right here we can also draw another interesting property. So if B and A are equal, so we could write A dot A. Yeah? So what is actually the dot product of a vector with itself? Just as we described before, we could actually write this as let me write it like the summation of AI, and I goes from 1 to the the size of the vector A, and that is 3. Like this is, we have 3 dimension here, so this is I from 1 to 3 in this case, but it can be any value if we have like more dimensional vectors, or sorry, higher dimensional vectors. But here I'm just talking about the 3. And this is basically the summation over I of AI squared, right? So, for example, if we have this 3-dimensional case of A times A, that means we write A of X squared, A of Y squared, and A of Z squared. And we learned also from the previous session that this is the magnitude of A squared. So in other words, if one wants to calculate the magnitude of a vector, then one has to basically calculate the dot product of A with itself, then take a square root of that, and then that is the magnitude of vector A. So previously I mentioned that if we have a vector A and a vector B, and these two have an angle of alpha with each other, the dot product of A and B, in other words, the projection of A on the B vector, would be then the magnitude of A, magnitude of B, and the cosine of these this angle that they make with each other. And on the other hand, we know from mathematics that the magnitude or the absolute value of cosine of each angle is always equal or less than 1. And now combining these two together, if we take the absolute value from both sides, then we can actually write that the absolute value of A times B is always equal or less than the absolute value of A multiplied by the absolute value of vector B. So we just said that the absolute value of A dot B is always less or equal to absolute value or the magnitude of A, and here the magnitude of B. And it turns out that this is a very interesting and useful relation, and this in mathematics and physics. And the name, there is also a name, maybe you you read it also in textbooks. The name of this inequality is called the Schwarz inequality. For now, maybe you just keep it in mind that the Schwarz inequality states that if you have two vectors and you take the dot product, the absolute value of the dot product of two vectors is always less than or equal of the normal multiplication of the absolute value or the magnitude of each of those vectors.